Swayam Prabha. Digital India. Educated India.
Now let's go ahead. So our aim is to solve this time independent Schrödinger equation. Why do you wanted to solve the time independent Schrödinger equation? In order to obtain the wave function and the corresponding energy. Let me speak now. I will take the answers. Otherwise time is going to be over and you will not be getting anything that is required. So our aim is to solve this time independent Schrödinger equation in order to obtain the wave function as well as the energy. So how do we compute the energy classically? We have discussed earlier. What is energy? Total energy is divided into kinetic energy and the potential energy. The moment you know the kinetic energy and potential energy, you know the full system. In quantum mechanics, the Hamiltonian operator, Hamiltonian H cap dot whatever you have seen, is called as the total energy operator. The moment you operate this total energy operator on the wave function, it will give you the energy and the wave function back. This is what is the time independent Schrödinger equation. What is the wave function? Wave function is like that x's and p's, positions and the momenta. Similar to that, the wave function will give you the entire thing. This is nothing but the state of the system. It will describe, like thermodynamics, you will use no state of the system. Same way, wave function tells you the state of the system. Therefore, if you use Hamiltonian operator on the state of the system, you will be able to obtain its energy. In general, we are always interested in the ground state energy. So why do we need to compute the energy? What is your answer for that? Why we are interested generally in energy?
So because the most stable configuration of any system is when its energy is
lower. That is great, but why do we want to calculate energy? That's the question I asked. Some purposes. Okay, fine, decent answer.
We calculate the energy so that we know how the molecule will settle, like eventually, because they will always.
So for a reaction to occur,
Yeah.
have you studied in thermodynamics some rule? Activation energy. Okay. When a reaction will be spontaneously occurring? What is delta G? Gibbs free energy. Okay. Now, if I wanted to understand whether a drug molecule will go and bind a protein, what kind of energy I need to calculate? Protein binding energy. Whether the drug molecule will go and interact with that or not, I will be seeing the protein binding energy. Someone said whether the molecule is stable or not. Delta G must be negative. That means in order to calculate that, I have to calculate what is called as the ground state energy. So like this, there are multiple cases. If you consider, energy is like ubiquitous in nature and you need to calculate that in multiple ways. This is one of the reasons we will be generally solving the time independent Schrödinger equation. Among the various states, like again, as you all said, ground state is one. There will be many excited states. People generally calculate the ground state because that is the first and simplest thing to calculate. Even that is not very simple, but that is something that can be calculated easier. When compared to the excited state, it is easier. Okay, so that's the reason we will calculate. So when you start studying quantum mechanics, what you will be first learning, like similar to ideal gas equation, you will see if I keep one particle and zero potential, what is the energy of that one? This is what is called as the particle in a 1D box problem. Okay, so when you solve this problem, the first nice thing that you will see is energy is quantized. The moment you fix a boundary, the moment you put a boundary to the system, that is you are keeping in the particle in a 1D box, you will have two walls which are having infinite height. And the moment you put a particle inside that, you will see that the energy of the particle is quantized. The energy is no more continuous. But the moment you remove the walls, the energy of the particle will be continuous. So that's the difference between classical and quantum. So when you are going to the quantum mechanics, what is happening? The atoms, molecules, these are all actually small sizes, right? Outside that vacuum, whatever you are seeing, you can think of like an infinite potential, whereas the inside one is the one that is like some confined place. The moment you confine any of these fundamental particles like electrons, protons, photons, etc., the moment you confine, you will see the emergence of quantum mechanics or quantization you will start seeing. This is the beautiful example that you will be learning the moment you start for the particle in a 1D box, where the potential is assumed to be 0 when it is inside the box. At the walls the potential is infinite. This is how you will be seeing. So it is like two big mountains are there. Here below there is a valley. If you put a particle inside that, how it would behave is the question. That's the question that we are solving for the particle in a 1D box. I will not be solving it here, but I am telling you this is what you will be learning. Essentially what you are going to get is energy is quantized. You will have a formula for the wave function. You will have a formula for the energy. Same way you can do for a harmonic potential. Instead of having two big mountains and one small valley, you can have a harmonic potential. The moment you have one electron or one particular particle inside the harmonic potential, how does it behave? This is the next problem that you will be studying. And so on and so forth, finally leading to the problem what is called as the hydrogen atom problem. Hydrogen atom also has how many electrons? One electron and one proton. That is where you will have the electrostatic interaction. Okay. So once you know this much, you will be able to solve and understand for the single particle how the quantum mechanics behaves. All this you will be solving by using the time independent Schrödinger equation, which is nothing but the H psi equals to E psi problem, where H is nothing but the Hamiltonian and Hamiltonian is nothing but what operator? Total energy operator. Containing total energy operator means what are the other parts of it? What are the parts of it? Kinetic energy and potential energy. These are the two operators that you would be seeing, and you apply them onto the wave function in order to get the energy. One way to see this is, I'll just come to another point. So once you solve these single particle systems, that's when you go to the next level, which is like having more electrons. The moment you have more electrons, you cannot solve them analytically. What is analytically versus numerically means?
Analytically is kind of formula for the system.
You said what? Logically, no. Analytically means you can solve it over pen and paper. You can get a formula. Okay. Whereas numerically means you don't have a formula, but you can use a computer to do some approximations and finally solve it. Okay. So you can solve, for example, helium atom numerically using quantum mechanics. However, analytically you cannot solve even a helium atom. The time independent Schrödinger equation that we have seen, you cannot solve it even for a helium atom, but you can solve it for a hydrogen atom. Again, I am emphasizing analytically. We do know the result, we do know the answer for the helium atom, but we don't have any formula to give it to you. Whereas for the hydrogen atom, we have the formula to give it to you. That's the reason when you saw the solved the Bohr atom, you know the energy levels and all the hydrogen atom spectra very much, exactly everything you know. Okay. So here I wanted to just show you a little bit. After this one. Okay. Just wait for a minute, because this will help you to understand and probably it will clear all the doubts. So Hamiltonian operator is nothing but the kinetic energy operator and the potential energy operator. This is how it will be. And you know that in quantum mechanics what will happen is, whenever you are considering an operator, can you awake her? She is peacefully sleeping. Hi. It's okay. Oh, okay. Sorry, I didn't understand that, because you are seeing that side, no? That's why I could not understand that. Fine. Okay, see here. So the kinetic energy operator, you know kinetic energy in terms of in classical mechanics? In momentum wise? P square by 2m. So in quantum mechanics, instead of writing p square by 2m, you will put this p hat square by 2m. In quantum mechanics, you will always put a hat to the people whoever are coming to you. Okay. Next, if it were a gravitational one, how do you write the potential? mg h. So mg you will not change anything, because these are like not the vectorial quantities. I am replacing it with x, so you will put an x hat. So this is how you will start writing. Okay. Anything. So if it were like a, you know that we are not dealing with heights here as essentially, but what we are dealing with is the potential, right? So let us consider the electrostatic potential. How do you write that? Electron and a proton, one positive charge, one negative charge, that are interacting with each other. How do you represent the potential energy? 1 by naught Q by R. This is the R is the position, right? This is what you would be writing in terms of the potential. Potential energy. Potential is what you have said. Potential energy will have Q square. Okay. So that is positive and the negative. Two of them are there. So therefore I will put a negative sign there. Okay. So you can write simply, if it is a one electron system and this is only one, you can simply write it as E square. Okay. In quantum mechanics again, this P is something will be represented as minus IH cross dou by dou x. This you can consider for the moment as a formula. Okay. When you get the time, you will be able to derive, but this you can consider as a formula or a postulate also. There is nothing wrong. I is the complex, yeah, number. So if I consider this way, using that one, can you tell me what will be the P square? Minus H cut square by dou square by dou x square. So whatever I wrote there is essentially for the x component of the momentum. So if I wanted to write all the components, what it will become? Minus H cut square plus dou square by how many of you are okay with this and how many of you are not okay with this? I will tell you. That's an operator. Oh, okay. So then that means IH cross dou by dou x, it should be that. Okay. Okay. H bar by I, right? So minus IH cross. I square is minus 1. Correct only, yes. Okay. So what we are essentially getting is an operator. So again, whenever we are saying an operator, it is going to operate on something, right? So he asked actually a good question. So what is this partial derivative acting upon? Okay. So whatever is there after that, it will act upon that. That's the reason it is an operator. Okay. So when we wrote H psi, H is the operator operating on the psi. Psi is the wave function. The moment it operates, it will yield you something which is the E and the psi back. Okay. So here whatever I have written is for the P square. So you know that kinetic energy term is nothing but P square over 2m. That is nothing but H cut square over 2m dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So the interesting thing or the simplest thing is, in quantum mechanics, whenever you are dealing, whatever you are dealing, kinetic energy will be always be looking like this. Because kinetic energy is not going to change. The only thing that can change is the mass of the particle. The operator form is exactly the same, always for you. Okay. So now if you have two particles, what will happen? Momentum will be described for each particle. So therefore, how many such operators you will have? Two operators, P1 square, P2 square. That's all. And the corresponding M1 and the M2 will be there. But this portion is always the same. Dou square by dou x square, dou square by dou y square. So the only thing that will be changing here is the M. Sum over I, Mi. That's all will be the difference. Now if you have 10 particles, sum is over from I equals to 1 to 10. We said earlier that I have n number of nuclei or m number of nuclei, I said I don't remember, and n number of electrons. If you are treating the electrons as quantum mechanical particles, accordingly it will be those many number of summation will be going from there to there. Okay. So this is what we will be dealing with when you are writing the system. So this is the electronic structure problem as a whole. So this whole thing you guys know about, I think this is called as the Laplacian operator, right? You might have heard of that. So the first term, Hamiltonian's first term here, whatever you are seeing is the kinetic energy of the electrons. So we have actually what you call used different units in order to make certain things go away. For example, here there is this ugly 1 by 4 pi epsilon naught term. I don't want to write every time that 1 by 4 pi epsilon naught. So we will call them atomic units. So we removed the 1 by 4 pi epsilon naught and we thought that it is equal to 1. Okay. This is for my what you call convenience. That's all. I can change the units back. Okay. So if you see that way, the first term has again mass of the electron will be there. Mass of the electron I am assuming as 1. Otherwise I have to put 9.1 into 10 to the power of minus 31. I don't want to take those numbers. So that's the reason I considered simply as 1 and I kept this. So now can you see that this is nothing but the kinetic energy of the electrons? The first term? All of you?
Yes.
Everyone is able to understand that is the first electrons. Second one has only ion masses. So this is nothing but the kinetic energy of second term is what? Kinetic energy of the nuclei. How many of you are unable to follow this? You are not able to follow. So what is kinetic energy? P square over 2m. You have written this one. This is for the first particle. So if I have 10 particles, what I have to do? I have to sum over all of them. Kinetic energy is a stabilization energy, so there is a negative sign for that. Okay. Sum is over. Small I is for the electrons. Capital I is for the nuclei. When I am considering the electron mass is 1, here I can keep this as 1. Then it will become minus h cut square by 2 into 1. H cut also I considered as 1 here. So the following quantities I am considering as 1. Mass of the electron is 1. A naught, the Bohr radius is also considered as 1. And there are a few more things we call as 1 for the atomic units. Okay, these are all called atomic units. So now can you see the second term? Second term as the kinetic energy of the nuclei. Who is unable to understand still? Please raise. I will try to explain. Everyone is understanding? The second term is the kinetic energy of nuclei. Third term is the electrostatic interaction between what and what? This R is nothing but the distance, right? When we considered Q1, Q square by R. This is Q square by R. R is the distance. Actually, there should be a vector. What is the distance? Distance between this positive and this negative. So this, whenever you are writing that, I can write it as, if I am representing the small r as the electron coordinate and capital R as the nuclear coordinate, the distance between them is what I have to write, and I can write it as r minus r mod, right? That's what is the distance. All of you are aware of this much?
Yes.
Notations? So accordingly, what is this one corresponding to? Electron nuclear interaction. Is it a attractive or a repulsive interaction? Attractive interaction. That's what I have written. So there you have Q square, right? Q I can write it as, if this is a positive nuclei, I can write it as Z into Q, where Z is the atomic number. All of you agree with that?
Yes.
E, I can put Z into E, and this is E. Again, another quantity that I wanted to put as 1 is E equals to 1 there. Okay. So if you see that way, then what is there? Zi by Ri minus capital R capital I. Following, not following? Everybody?
Yes.
So this is the attractive energy. The next one is about, what is that energy? Electron repulsive energy. And the next one is nuclear repulsion energy. So this is the Hamiltonian. Is it easy for us to understand?
Yes.
So the entire Hamiltonian is divided into kinetic energy and potential energy. Kinetic energy of the nucleus, potential energy between the electron, nuclear, electron. This is the interactions that we have. If there is light, you have to add what is the potential that the light is interacting with. That is again additional potential energy. But the kinetic energy part is very simple for all of you to write. Okay. So the moment you have written this, what is this? This is actually a differential equation. If you see here, you know that this is a differential equation. The moment you have a differential equation, if you wanted to solve, you need to have the boundary conditions. Right? The moment you solve the differential equation, you will get a solution. That solution is nothing but the wave function for us. Are you understanding? Schrödinger has devised a differential equation. If you solve this differential equation, what you will get? The solution. That solution is the wave function. On the other hand, Heisenberg has started with matrices. If you again diagonalize that matrix, you will again get a solution, those eigenvectors. So those are also nothing but the wave functions. So one is in the matrix mechanics, another one is the wave mechanics or differential equations. Since you will be generally, I mean in olden days, the methodology is first you will be taught the differential equations. That's how the Schrödinger equation had become famous. Matrix mechanics came much later. Okay, that's the reason matrices were not taught. Probably now you were taught with matrix mechanics also. So you can actually start with Heisenberg picture also, but generally the Schrödinger picture is what will be taught to you. Okay, any questions here? Why are we? Why are we diagonalizing the matrix? So the major reason is like in order to identify the eigenvectors. Why we are interested in the eigenvectors is they are the vectors when you are considering the measurements. These are the outcomes. So when you are like someone said about the superposition, right? So when you are considering the system is in a superposition always. System is always in a superposition. What does that mean? System means wave function. The wave function is in like a wavy nature kind of a thing you can think of. The moment you operate this wave function, it will fall onto one of these eigenvectors. I'm repeating one more time such that it will go inside you. So you consider the wave function, okay? So this wave function when you are operating or measuring, the moment you measure the wave function, it will collapse. The wave function will collapse. Collapse to what? Collapse to one of these eigenvectors. Okay, that's the reason you are diagonalizing to know what are the eigenvectors.
Diagonalizing is equivalent to
collapsing the wave function into eigenvectors. You are identifying what are the possible states that you can measure. So the wave function is always in a superposition. Only it will come to a specific state when you are measuring. If you are not measuring, the wave function is there somewhere. In what state, what it is doing, etc., we don't know. When you wanted to know what is the state of the system, you have to do the measurement. The moment you do the measurement, you are forcing the system to come down to something. What it is coming is one of the eigenstates. It is called as the eigenstate. Okay. Among these eigenstates, which state it is generally coming? If in general, in order to know what is the ground state energy, you have to prepare the system and measure its ground state energy 1000 times. When you do the 1000 times, which state it is falling into is what is going to give you that particular state's energy. That's what you are calling actually as the ground state energy.
Sir,
I need to actually finish that computational way of teaching you the.
Sir, I have a doubt.
Fine.
Sir, how is dou by dou x whole square is not the same as dou square x by dou x square? We are applying the P of P.
Is it d by dx? Again, you apply the d by dx. What will happen?
Sir, I get the fact
Sir,
that
but
d by dx or d by dx is d square by.
That's what we are doing.
Sir, but when you whole square it, sir, d by dx whole square is not the same as d square by dx square.
Here in this case, d by dx into d by dx.
Imaginary fact.
Okay. So, okay, we can further discuss these things. Can we move ahead quickly to finish the part? Otherwise, like I will not be teaching you the main part, any part. Okay. So what we have done here is like to come back from this, there is some approximation. So although this is the equation that you need to solve, or this is the differential equation that you need to solve for, this differential equation you can never easily solve it. So therefore you need to go for the approximations. One of the first approximation that you are going to deal with is you understand that the nuclei are very heavy when compared to that of the electrons. Nuclei are heavy means how much heavy they are. Do you know the mass of the proton versus the electron?
Yes. 1.6 in 10 power minus 21.
In ratio.
10 power minus 21.
1837 or something like that will, okay, so it's close to 2000. If you consider carbon atom versus electron, it is something like 20,000. Carbon atom versus electron, if you are considering, it is 20,000 times the difference. It is like 1 gram versus 20 kgs. That's the difference that we are speaking. So therefore you can safely imagine in general that when the electrons are moving, nuclei are somewhat more or less like static. So that's the approximation which you can see, that is called as the Born-Oppenheim approximation. Essentially it is telling you that the nuclear degrees of freedom and the electron degrees of freedom can be separately dealt with. Instead of dealing with both of them at the same footing. So that when you are considering the nuclei are static, obviously the kinetic energy of the nuclei will be considered to be, if the nuclei are static, what is the kinetic energy? Zero. And this is nothing but a constant, because nuclear static means I can easily write a formula and I can simply calculate the electrostatic interaction between a set of nuclei. That's what I am doing, and this is what is called as the electronic Hamiltonian. And in general, this is what we will solve on a computer or anything. Okay, I wanted to tell you this much, that what we are solving you should know. So we are solving only this particular portion whenever we are solving for the energy. So when I speak of ground state energy of a particular system, this is what I am calculating. Okay, so with this introduction, I am going into the topic that we are dealing with. Okay, so let's go ahead quickly. I will skip this part right now. So what is our title is to calculate the how do you calculate the properties of a good anode material. So now if you pay full attention, I can actually cover this in 10 to 15 minutes, but I want your full attention. Okay, and do not disturb me unless it is really required. Okay, so let's see. So why do we study the energy storage devices? You all know about this Russia-Ukraine war and how India faced issues in between. So when America put sanctions on us, we need to get the oil from somewhere, because it is our need. Our population is so high and our energy demands are so high. So the moment you rely on something like oil, this is what will happen. So therefore there is a need for all of us to go towards the renewable energy resources, and it's not a new idea. People have been working on the renewable energy resources, and this particular plot is at 2021, but you know that already there is a huge amount of demand is increasing for the renewable energy resources. People are using them like solar, wind, etc., etc. In India also you are seeing that. The issue with the renewable energy resources is, unlike the oil or the petrol, whenever you wanted to use, it is not feasible for you. For example, if I want to get the solar energy, now it's a good day, I am getting the sun today, but yesterday if you saw, it was like little bit shady. So therefore, I cannot get the renewable energy resources whenever I want. Same goes for the wind or hydrothermal or geothermal, any other kinds of things. If you see, there are like either location dependent. So if I wanted to create a hydrothermal project, I cannot create in Chennai. I need to find it a good place where there is a good flow of water, and surrounding there should be some big mountains, so that I can store the water easily. So similarly goes for the geothermal plants, anything that you wanted to consider. So therefore all these renewable energy resources, if I wanted to use them, the main point is I cannot use them continuously. But the issue with that is, if I wanted to have fan right now, if you say that okay, tomorrow morning I will give you the fan, will you be happy? No, right? So when you wanted to switch on the light, you wanted to switch on the light, and when you wanted to switch off, you wanted to switch it off. That's all it is. So in order to do that, what you need to do, since energy that is coming from the renewable energy resources is not continuous, you wanted to first store that energy and utilize that energy when you want. This was the case that our ancestors used it to do. Right now we have like surplus amount of food, so we never bothered about it. But earlier days, people used it to store a lot of food. For supplies used to be there, this achars, etc., that they use it to make, in order to ensure that when you do not have any food, you will at least eat with that rice and this achar, such that you will be happy for that day. So that the way we need to store the energy. So what is the ways to store the energy? There are multiple ways to store the energy. One of the best ways is the portable batteries or rechargeable batteries. Among the various kinds of rechargeable batteries, lithium-ion batteries are at the forefront. Again, I skipped one entire section of comments of what you can do as a storage. Okay, there are multiple ways of storage. You should at least try to search in the Google what are the storage. There are rotational ways, rotational kinetic energy. You can turn the turbines and you can save the energy, store the energy, etc. Mechanical ways are there. This is the electrochemical way of storing the energy, but there are mechanical and various other kinds. Please try to see how do you store the energy. Among the various ways, lithium-ion batteries are at the forefront. Okay, again, as I said, there are multiple rechargeable batteries, lithium-ion, nickel-cadmium, zinc-air batteries, and so on and so forth. There are various kinds of batteries, sodium-ion batteries, magnesium, etc., etc. So lithium-ion batteries are at the forefront because the discovery was earlier, and also because of their portable nature and the cheap and availability, etc., etc. So what is the issue with the lithium-ion battery? So the principle of the lithium-ion batteries is very simple, or any other batteries also will be roughly the same. So where you will have a cathode and an anode. Here the anode material is shown as the graphite. So during the discharge, what will happen? So the ions which are there, that will be flowing from one end to the other, and during the charging time, this will be moving from the cathode to the anode, and during the discharge time, from the anode to the cathode they will come back. So discharge is like the thermodynamically most stable side, stable one. Therefore, when you are keeping this lithium ions in the graphite, they will slowly come from the graphite towards the cathode. Here the cathode material is some lithium cobalt oxide. All of you are with me till here?
Yes.
Okay. What is the principle? As I said, during the charging, you will be pushing this lithium ions which are there in the lithium cobalt oxide into the anode material, which is the graphite kind of a thing. So you can think of this as something like pumping the water. Okay. So you have a tank up and you have some water which is there in the ground. You are using the motor in order to pump the water from the ground to the tank. So this is like thermodynamically uphill process, right? So that's what is called as the charging. That's why you need to get it into the socket, because you are taking the energy from outside in order to charge this. But if you wanted to just use this material, all you need to do is open the tap. That is, you are touching your mobile phone there. So that is the discharging, where the ions will start coming from the anode material towards the cathode. Is this clear till here? So the issue with this is, I mean, lithium ions among all the other ones, lithium ions are still at the forefront, but the issue with that is the energy density of the lithium ion batteries is still low, okay, the current ones. So we wanted to improve the lithium ion battery energy density, because why you wanted the energy density means, you understand density, right? Energy density means energy stored per unit volume. So if you are taking a car, you don't want the batteries to be entirely filled by the car, right? You wanted to store your own luggage, you wanted to sit in the car, and you wanted to take your friends, etc., right? And the weight of the car should be very low when compared to the other things, that the cargo that you wanted to take. If the car itself is very heavy, then it is essentially like, if you are driving, you are essentially, the fuel is wasted just for the car itself, right? So considering all that, here the major point I am trying to tell you here is about the energy density. The energy density is very little here, therefore the how much amount of energy that can be stored is less. That means if I wanted to go for long distances, let us say that I wanted to go for 300 kilometers or so in my car, I cannot at a stretch go, and I have to go and stop after 100 kilometers and again do the charging, which is not what I want in general. On the other hand, if I fill my gas or petrol, I can go for easily like 300 to 400 kilometers by filling the 21 liter tank that I have, right? So that is much easier for me. So therefore I need right now, if I wanted to completely consider an electric vehicle for very long distances, or if not just for the cars, if I wanted to have an aeroplane that will just simply run on the electric parts, then what I need is something with very high energy densities. For high energy densities, what I need to consider alternate materials. Apart from this particular issue of the energy density, you also know that the raw materials that we have, we do not have the corresponding raw materials in, for example, in India. What are the raw materials? Lithium cobalt oxide, I said. Neither lithium we have, nor the cobalt we have, nor the nickel, nor the manganese, etc. So therefore, what is the issue with this kind of an approach? We are again going back to the square one. Earlier, why we thought that we will come back to the renewable energy resources? Because non-renewable energy resource, the oil, is not there in India. We have to rely on the Russia or the whatever, that United Arab Emirates or any other person. But right now, you are thinking that, okay, I will go for the renewable energy resources. In order to use the renewable energy resources, what is the story for us? You need to store the energy, but for storing the energy, you need some materials. That materials are not there with you again. Again, you have to go back to the China and ask for the lithium, or you have to go to Argentina and go and ask for the lithium, or to Africa for cobalt, etc., etc. Again, we have to rely on someone else. The actual solution, this is like for my talk, I will be telling about the story about my talk, but the actual solution truly is going towards the nuclear energy. This is the fact, okay? But however, like the moment we hear nuclear, somewhere deep down we all remember that Hiroshima and Nagasaki incident, and we never wanted to go towards the nuclear part. Probably if you have seen few more videos, you might also know about the Chernobyl incident. Okay, so he watched so many videos, so he knows more. So, but the point is, we are all scared. But the truth is, if you go to the nuclear energy, it's the safest one actually. It's the cleanest one. It's sustainable. Okay, all you will get is only little bit amount of nuclear waste that you can actually fill in the land, and you will be safe. But we did not educate the society in such a way, therefore we are suffering right now. Okay, and it will continue easily till you grow and you become professors or whatever. I don't think it will be changing in the next 30 years or so, but the best approach would be to go towards the nuclear. But since we are anyway not going there, we are continuing with the presentation. So we will be anyway dealing with the lithium-ion batteries, etc. So you wanted to find the alternatives. So what are the alternatives? You can consider sodium-ion batteries, potassium-ion batteries, calcium-ion batteries, magnesium-ion batteries. Name one, I can make it. Okay. So all these batteries are there, but the important issue is all the battery technologies are not the similar. That means the moment I have lithium-ion battery technology, I have mastered it, for example, today. But the moment I wanted to go to the sodium-ion battery, I have to again rework on my anode material, my cathode material, my electrolyte, my separator, my current collector, etc., etc. The things that are worked for one particular battery material will not work for the other, because the chemistry, battery chemistry is completely different. Therefore, you have to work on these things. So as I said earlier, for the case of lithium-ion batteries, people found that graphite is the best material. Graphite is nothing but layered material. Layered graphene sheets are there. That's what is graphite. So what are the alternate materials we need to find is, so one part you can think of is, I wanted to replace graphite in the lithium-ion batteries and see whether I can get better, or I wanted to completely replace the lithium-ion batteries, I wanted to go other ion batteries, for which what are the alternate anode materials. These are the two ways you can think of. We thought in that manner and we tried to find out other anode materials. Okay, this is not something like really difficult science. This you can also, if you spend some 3-4 months in my lab, you will also be able to identify new anode materials that can be useful. So what are the properties of these anode materials that we can calculate is what I am going to show here. So first I need to understand whether this material is stable or not. Stability means thermodynamic stability I can consider. Also what is called as the dynamical stability, mechanical stability, thermal stability. I hope you heard these words. I said very quickly. Okay, so these are all like thermal stability means I will heat the system and I will see whether the system is stable or not. Mechanical stability, I will push something and I will pull something and I will see whether the system is stable or not. Similarly, there are dynamical stabilities about the, I will displace the atoms and see whether the structure is stable or not, etc. Okay, so if the material is stable, then I can think of whether it is a metal or not. In general, you know that anodes or cathodes, these are electrodes. These are actually metals. If they are metals, they will be able to conduct properly. If they are not metals, we will add some current collectors, etc. Still, we will be using it. But if that is a metal, it will be nice. So that's another thing that we will be doing. After that, I have to calculate about the affinity towards the metal atom. So if I have this anode material, I have shown you earlier, during the charging, what will happen? From the cathode, this lithium ions or whatever the ions that we are considering, they have to flow through the liquid electrolyte and they have to reach towards the anode and they have to stay there. They have to stay there means like when you are pumping the water, there should be a tank. Then only the water will be staying there. If it is like your whole roof, you kept it there, what will happen? It will be simply filling and falling down. Okay, so you need to have some affinity to the water. Here it is affinity towards the metal atom. So if that is there, how do you do that? You have to calculate what is called as the adsorption energy. Okay, we said earlier we wanted to calculate energies, right? So this is one kind of energy I need to calculate. Similarly, I need to have low anodic voltage. So if you consider about the total cell voltage is defined as the cathode voltage minus the anode voltage. Since if I have high voltage I can produce from the particular system, then my energy density can be improved. Okay, so therefore I wanted to have high voltage. If I wanted to have high cell voltage, I have to have low anodic voltage. So that is another condition that I have to see whether my anode material works or not. After that is about the low migration energy barrier. I will answer all the questions.
So what is the reference electrode?
we can consider various electrodes. In this particular case, I am only dealing with anode material. I am not worried about what is the other side. Okay, we can consider various materials will be there. So other one is about the low migration energy barrier. Why am I saying the migration energy barrier? You remember, right, again this picture where ions will be flowing from the cathode to the anode. So when first one will go and sit there, but what happens to the next one onwards? They have to adjust within the space that is available. For that, the ions have to move. If the migration energy barrier is very high, this will be what is called as the over potential. So you have to give extra potential in order, extra bias or extra energy you have to spend just to move the atoms or to remove the atoms. Therefore, if the energy barrier is less, they can simply hop there. I don't need to waste my energy in just charging and discharging. Rather, I can utilize the energy. Finally, I have to consider about low structural distortion. If the structure is distorted during the cycles, like every cycle means I have to put the things, I have to remove the things. If it is corroded or if it is happening something, then I cannot utilize this for long duration. You don't want to change your battery every 2 days, 3 days, right? Like if you buy a mobile, you wanted to keep it at least for few days. Unless you are a fashion freak and you are changing, that's a different story. But if you are like a frugal person, at least you wanted to buy a mobile and use it for at least 3-4 years, right? So that's where if the structural distortions are heavily happening, your mobile one day will be flat, another day it will be changing into a different structure, which you don't want, okay? So such kind of things you don't want. So these are some properties that we are calculating on a computer. These are only some properties. There are various other properties that we can consider, calculate and finalize. But these are certain properties that you can use in order to say that whether an anode material is a good anode material or not. Okay. So from here I will take maximum of 5 minutes to show one specific example of what is the material that we considered, how we've identified that it is a good anode material or not. So how much time I have, madam? Backside? Okay, but we started at 9:15. It is fine if I take 5 to 10 minutes more?
Yes, sir.
Students?
Yes, sir.
Fine? Okay, cool. So, there are again, as I said, there are several 2D materials that are available. What we considered is like recently someone found some 2D material. We wanted to test whether they are good for anodes or not. This is my interest. So, these materials are called as anti-maxines. These are called anti-maxines because someone else previously discovered what are maxines. So therefore they identified what is the anti-maxine. Okay, these are all nomenclature essentially. So maxines means this max phases. They will have this M is corresponding to transition metal, A is corresponding to alkali and alkaline earth metal, and X is the non-metal. Example, if you consider titanium, you know as the transition metal, non-metal is the carbide, and the alkali metal is the aluminum. Okay. This is only an example. So this is the structure of an maxine material. Anti-maxine will have the non-metal in the, so this is only two of them are there. This cobalt arsenide, cobalt boride, etc. These are called as the anti-maxines, where you will have only like this. So there is a metal, the blue color element that you are seeing is the cobalt. On the top and bottom you have the non-metal. In the maxines, what happened? Metal is there at the top and non-metal is there in the middle. All of you, again, in the maxines, what is there? Metal is there at the top, non-metal is there in the middle. Therefore, metal is there means which ones are reactive? Non-metals are reactive or metals are reactive? Metals are more reactive, that you know. Therefore, they formed these carbides, arsenides, etc. on the top, if you see. Okay. They thought that okay, let us change the composition, let us try to peel it off at the separate place so that we can get the anti-maxines and we can use them. So this is what are the anti-maxines are made up of. Okay, so here you have on the top and bottom different kinds. Arsenic is there, boron is there, phosphorus is there, sulfur, selenium, silicon, etc. So these are the materials. So these people whoever have discovered earlier, some Chinese names, Gu et al. So they have discovered something like all those 20 or so materials they identified. They are very good materials. Anti-maxines is what they said. So what we thought was, okay, they have identified 21 materials. These are two new dimensional materials. Let us consider some of them and see whether they are good anode materials or not. This is what our project was at that time. So we considered all these 6 materials and we studied them. Okay. Don't ask me why you did not study this. I can study that, but I have left it for you people, whoever is coming and joining and studying, okay, like that, okay. There are many 2D materials, we have studied some of them. So first thing is dynamical stability. So in this, I cannot explain everything to you that much easily, but the answer to this is, first one, as I said, if you are displacing the atoms, you are trying to see how the phonons are behaving. Have you heard of phonon also?
Yes.
So in this is called as phonon spectra. Phonon spectra, in this is called as. So if you find anything negative in this one, any line that comes negative, that means it is not stable, okay. So in this one, as you can see, everything is on the positive axis side. So you can accept me and you take my word that these systems are stable, okay. Next one is about why they are stable, is what we have studied. So you know about this ionic interaction, covalent interaction, etc. So we have plotted what are called as electron localization functions. Again, these are just words for you at this moment, but essentially it is showing you where the electron density is there. So you can see that majority of the times it is there like on the non-metal atom, the central metal atom. You can see green color, etc. are corresponding to non-metals. Only the blue color is the cobalt. You can see in majority of the cases the central place is there is nothing, right? So this means it is more like an ionic interaction where the electron cloud is there onto this arsenic, boron, etc., etc. How this material is stabilized? These materials are stabilized based on the ionic interaction between the cobalt and the other one. This is the first inference. Next part, whether these are metals or not is the question. So for this we calculate what is called as the band structure. How many of you heard of this word band structure or bands, band theory?
Electron band valence.
That one only, this one, okay. Okay, so you know that if there is a gap between the conduction band and the valence band, if the gap is little, you call it as
Conductor.
it's called semiconductor, okay. It's not fully conductor. If there is no gap, you call it as a
Conductor.
metallic system or a conductor. If the gap is very high, insulator. Those two people are happily speaking. I don't know what they're speaking. Hi. Okay, so if you see here in this particular band structure, this is left side one is called band structure, right side one is called as the density of states. So you can see here near the Fermi level, the bands are crossing, okay. So this dashed line which you are able to see here, this dashed line, horizontal line, this is called as the Fermi level. So below that is called as valence band, above that is called as the conduction band, and you are seeing that the bands are crossing near the Fermi level. Therefore, there is like finite amount of energy levels are there at the Fermi level. Therefore, these are called as which systems? Metallic, semiconductor, insulating.
Last thing is finite number of lamps
Near the Fermi level. Why semiconductor?
conductors.
Finite number are there already. There is no gap between the conduction band and the valence band. So finite number of states are there means there is no gap essentially. Since there is no gap, these are metallic system. You can check for each one of the system. There are some finite bands here, finite bands here, finite bands here, here, everything. So all these systems are which systems?
Metallic.
So therefore I am satisfied that I can start with these materials. I am thinking that whether these are useful for anode materials or not. First I checked their stability, they are stable. Next I check for the electron, whether they are conducting people or not. They are conductors. So therefore I can safely start with them. Next thing is what I said, affinity towards that. So that means I have to calculate the adsorption energies. I have calculated and I have shown the numbers here. How many of you are able to see from the back side? Are you able to see the numbers? Yes? Okay. If you are not able to see, at least see the negative sign is there, okay. That means they are stable, having some energies in the range of, so for the case of this S3 site, so this is like the cobalt anti-maxine. So in this there are several sites. When I am saying adsorption, this is like a surface is there. Surface will have various sites to sit, like how you are sitting at various places inside this room. So I have to find out which position is the most stable position for that particular system. For him, this might be the most stable position, but for that other girl, that backside seat might be the most stable position. Similarly, for lithium, one point might be the most stable, but for the sodium another point might be the most stable position. So for each of these atoms I have to calculate what is the most stable position on this cobalt particular anode. If I change the anode, positions will change. If I change the metal atom, positions will change. For teachers, back bench might be better. For students, might be front benches are better. It depends on the person to person. Similarly, based on the material to material as well as based on the room also, right? So all these things we have to consider. So we have considered here 6 sites. Among the 6 sites, we found that this S3, S1 and S2, these 3 sites are the most stable site. Among these 3, S3 is the most stable one. So therefore, if I am just taking a bunch of sodium atoms or lithium atoms and I am sprinkling like this, many of them will go and sit at the S3 side because that is the most stable side. This is what we are expecting, okay? What happens in reality we have to further see, but this is what is based on the computation. So similarly I did for lithium, sodium, potassium. Fortunately for all 3 of them, we found that the S3 site is the most stable site. So immediately the question will come. What is the question? Why S3 site? Wonderful. That's all we also asked the question. And we plotted the charge density differences, okay? So that means charge density difference means what I will do is, I have this anode material, I kept the metal atom at the S3 site, S1 site, separate sites. So let us consider that I kept it at the S3 site. I take this full system and I solve the time independent Schrödinger equation. I will get the wave function of this. I remove this one and I solve the time independent Schrödinger equation. Again I will get the wave function of this. I remove this material but I keep this atom here and again I will do the time independent Schrödinger equation. These are 3 different things. I subtract, this wave function is nothing, it doesn't have any physical significance that you might have remembered. Mod psi square is the one that is having this physical significance. So you calculate that mod psi square and subtract the total from the individual ones. So this will tell me how the electron distribution is changed or the charge distribution has changed. So I have shown you here the charge depletion sites and charge accumulation sites. Magenta is the charge depletion, this one is the charge accumulation. So charge is depleted from the metal atom and it has gone to the anode material. And here you can see that this particular atom at S3 site is bonded with 4, whereas at S1 site it is bonded with 2 atoms, whereas at the S2 site it is only bonded with 1 atom. So therefore, can you expect which one should be more stable? Okay, that's all we also said in that article. Okay, fine. You can also do this work. Good. Next, so we understood that S3 site is the most stable site. Next, we try to understand the migration energy barriers. Again, migration energy barrier means we said that S3 is the most stable site. So therefore, I have to move from one stable site to another stable site during the charging and the discharging. So there will be multiple paths. If I wanted to go there, I could have walked on these tables, jumped and go there, or I would have moved like this, or I would have gone like this, etc., etc. Since these are lithium atoms, they don't have any culture or something like that, right? So they can go in any form. So I have to test what are the possible forms it can go and identify what is the best possible form. So what is their way of going? They will try to go through whatever is the minimum energy. If you have seen water, if you just pour some water here, where it will go? Whatever is the lowest potential, that is that path only it will go. So if there is a downhill, it will just follow through that downhill. But if there is some little bit changes are there, it will try to follow that one, how the rivers are flowing, etc., etc. Same way they will do. So what I need to identify? I need to identify that particular path through which the energy is minimum. Then it will follow. I know that that's the path that it will be following. So I have specifically considered 3 paths here. You can consider little more paths also. It doesn't matter. So among these paths, we found that this path 3 is this one, and path 1 is the one which is having the lowest energy. Okay. So path 2 we could not stabilize. Whenever we tried to ask the metal atoms to go along path 2, they just fallen back to the path 1. Okay. So again, I have identified path 3 and path 1, and I found that path 1 is the most stable one for all the 3 cases. What is the next question?
Why path 1?
Obvious question. Okay, one is why path 1. Next question should be, if you see carefully, lithium, sodium, potassium, they are behaving slightly differently. Why lithium has the lowest barrier when compared to sodium? Whatever, in this case it is showing potassium. Potassium has the lowest energy barrier when compared to lithium and sodium. So the 2 questions that we need to ask are, why path 1 is more stable? Second one is, why potassium is having the lowest energy. So both of them again you can explain based on what is called as the differences in the adsorption energy. So we have done this particular part and we also identified. So the first thing I wanted to bring back to your attention is this one. So among all of these ones, I think some of you at least read. Can you read the binding energy for the case of lithium?
Minus 1.5.
Minus 1.5. Sodium
Minus 1.5.
and potassium.
Minus 1.6.
So in this I can arrange that potassium is having the highest adsorption energy. That means it is binding strongly or weakly? Strongly. The potassium atom is bound strongly to the anode material, right? So now if you see the migration energy paths, you can see here even much more clear for all the cases we have done. What you are seeing, this is for the lithium, sodium and potassium. Which one has the least migration energy barrier?
Potassium.
Potassium. Is it a counterintuitive one or a proper result? Why?
It's more strongly bound, but it's more easily moving.
It's strongly bound but it is easily moving. So where it is going wrong? What do you think could be the reason? The results are correct. There is no doubt about that. These results are also correct. Adsorption energy results are also correct. Whenever we say counterintuitive means what is wrong? Our intuition is wrong, right? That's what it is counterintuitive means. So where our intuition is going wrong? Our intuition is going wrong because we are assuming that once it is adsorbed, I have to fully remove and again fully place that. You are saying that because it is strongly bound, its migration energy barrier should be low. But migration energy barrier is telling about what? I have two sides like this. I am jumping from this side and coming onto this side. That's all. So this is like you can imagine two valleys are there. I have to cross this valley and reach here. I don't need to be removed into the gas phase and again I have to fall down here. Are you following?
Yes.
So I have this much small barrier is there. All I need to do is cross this barrier and go there. So how to identify this barrier? All I need to see is the difference between the potential energies at this place and this place. If I understand this, I do know the difference. Are you following? So let us go back to that particular one and see one more time. I might have given here. I have given here. So you can see here. Let us concentrate on the last one, but you can take any particular thing and you can do. Those who are doubtful about me can take anything. Those who believe me can go through the last one. So you take the difference between S3, S1, S2. Why I consider S3, S1, S2 is that is the path here. Okay? S3, S1, S2 is the path that we are considering. So if you consider S3 to S1 to S2, what is the difference between this one and this one? 0.15, 0.7, 0.8, 0.7, 0.03, 0.7. Okay? So you consider like this for the potassium. 1.6, 1.2, 0.4, 1.2, 1.9, 0.3. So where the difference in the energies between potassium sites S3 to S1 are lower, whereas for the case of lithium are higher. And if you see actually the barrier heights are also roughly the same. If you see here, that is around close to the 0.4, whereas here it is close to the 0.7 to 0.8 range. Okay? Is this clear? So then we calculated the migration energy barriers and we found that this is entirely like if you just try to calculate for each and every step, this is exactly what you will be reproducing. Essentially, it is telling you that you need to consider the differences in the energies between these two states in order to understand them. Fine. So this we did, and then we calculated the voltages. This kind of equations, you know, when you add the electron, how much is the potential energy difference, reduction potential you call it. So that way we have calculated, and we again considered the various other things. I'm trying to skip because already time is shooting up, and we calculated these voltages based on the adsorption energies, etc. And we found that the average voltage is coming closer to the zero. Again, that is good result for us. Again, as we said, if the anode voltage is very low, then that means it will be helpful to create the overall cell voltage to be more. Similarly, we calculated what is called as the specific capacity, and the specific capacity generally for the lithium-ion batteries is close to 300, and when we considered, theoretical capacities, whereas we got up to 1000. Okay, suggesting that these materials might be very much useful if we are using it for the lithium, sodium and potassium ion batteries, specifically for the lithium-ion battery. Then we tested the thermal stability. Thermal stability is also good. You can see that this is the starting structure, this is the final structure. Are you able to see any great differences between them? No. And we ran it for some 15 picoseconds also at 300 Kelvin. Seems like good. Same for the other anti-maxines. And we tried to identify why these systems are stable also. Again, based on the electrostatic interactions, we were able to tell that why that is actually stable. Similarly, we tried to understand the expansion. The expansions are also roughly the closely whatever we were expecting. So based on this, the conclusion is the newly developed cobalt anti-maxines can be used as the anode materials for the next generation batteries. Okay. Now, I mean, you can read out all the other conclusions, but that's where I wanted to thank you for your attention.
Swayam Prabha. Digital India. Educated India.